Three-phase motor connection in refrigeration. Thanks for being with us. First we are going to understand the operation of the three-phase motor used in refrigeration, either in compressors, pumps and fans. Let us first study these three fundamental concepts. 1. Induced magnetic field. 2. Magnetic induction. 3. Lenz's law. Well then, let's get started. 1. Induced magnetic field. A current flowing through a conductor generates a magnetic field around it. The direction and sense of the magnetic field around a conductor are determined by the right-hand rule. The magnetic field produced between two turns is similar to that produced between two parallel conductors whose currents flow in the same direction. In reality, the field induced by the current that crosses the conducting wire is the same. What happens is that the geometry of the coil makes it concentrate in the core. 2. Magnetic induction. Magnetic induction is the process by which magnetic fields generate electric fields. When an electric field is generated in a conducting material, the charge carriers will be subjected to a force and an electric current will be induced in the conductor. In our case, if we have a conductor near the coils, through which alternating current passes, the magnetic field of these coils produces current in that conductor. For a three-phase motor, we have three static coils, which cause magnetic fields that change synchronously and induce electric current to a conductor that is coupled to the rotor or shaft of the motor. At this moment we must ask ourselves, how is the new induced current that was generated in the conductor coupled to the rotor? To understand the particularities of this new current, we must base ourselves on Lenz's law. This law indicates that the induced current in a circuit will have such a direction that the magnetic field generated by said current compensates for the flux variation of the magnetic field that has generated it. Now we have two types of electric currents. A. The electrical current, which is passing through the static coils, which comes from the electrical network. B. We have the induced electric current that passes through the conductor coupled to the rotor and that was generated by the magnetic field of the static coils. Analyzing, as any current that passes through a conductor generates a magnetic field, then the new induced current of the rotor has also generated its own magnetic field. Now let's imagine that the rotor conductor is also shaped like a coil, so that its magnetic field increases. So now we're talking about, we have two very strong magnetic fields. A. The magnetic field produced by the static coils, due to the passage of current from the electrical network. B. We have the magnetic field, from the conductor coupled to the rotor, which is now strong, because we have also shaped it into a coil. It happens then that the currents in the rotor, when interacting with the magnetic field of the stator, originate torque forces in the axis of the machine. By Lenz's law, mentioned above, this force will try to reduce the magnetic flux variations in the rotor winding, and therefore will try to make it rotate, at the same speed as the rotating magnetic field, but never succeed. The speed of these machines is therefore slightly different from that of synchronism, hence their name is asynchronous. On the other hand, the currents that circulate through the rotor appear by electromagnetic induction, hence its other name of induction motors. Star connection of the three-phase motor. This type of connection is limited to low-power motors, such as fans, pumps or small compressors, since higher power induction motors using this type of starter need a lot of current to start. In other words, we are lowering the voltage applied to the motor and the current. The connection in this case is made as shown in the figure. Direct connection of a three-phase motor in triangle or delta, that is, the maximum voltage. The end of one coil is joined with the beginning of the next and thus the three are joined. The current through the circuit is maximum. This connection can be used for motors with low power and starting torque. It is made as shown in the figure. Starting method, star delta. 2. It is used with the objective of lowering the starting current at the beginning of the connection.
D.
To do this, the coils will be momentarily connected in low or star voltage, and when the motor shaft reaches 80% of normal speed, the coils will switch to maximum voltage delta connection.
C.
This type of connection is only used for motors that do not require as much force to start. D. To use this type of starter, the motor must be capable of working with both voltages.
And,
as a rule, the commutator, which changes from star to delta, must change the connection when the motor stops accelerating, that is, when the current consumption of the motor stabilizes. F. Use the clamp meter to measure when the current is stable. Count the time with the stopwatch and set the switch. The split-winding three-phase motor for winding. This motor is characterized by having two parallel winding systems in the stator, which can be internally connected in star or delta. Equivalent to two motor means. The two winding systems can be the same or different. The winding ratio will indicate the installation procedure for starting the compressor. This type of motor can have 6 or 12 output terminals, the first being the most common. During starting, a single motor half is direct coupled at full voltage to the mains, which splits both starting current and torque. However, the torque is higher than what would be provided by the star-delta starter of a column motor of equal power. At the end of the boot, the second winding is coupled to the network. At this time, the current peak is weak and short-lived, since the motor has not been separated from the mains. When you have a part-winding type motor with 9 terminals, we have to know that one of the windings is internally connected in star, and the other is not connected, and we must connect it ourselves. 2. If the three-phase current is 400 volts, a star circuit must be built with coils in series, whose center of the star will be the star circuit that comes attached from the factory. D. The idea is to form a star circuit with 2 coils at each end. For this we must attach the coils that are not connected. C. Now as the connection is star, low voltage. D. That is, if the three-phase connection is 400 volts, because it is a star, this voltage is divided by the square root of 3, leaving a 230-volt circuit. E. As each leg of the star has 2 coils, this 230-volt voltage is divided by 2, leaving each coil of each leg of the star with approximately 115 volts. Now if the three-phase connection is 230 volts, in order to supply a voltage of 115 volts to each coil, we must build 2 independent stars that work in parallel. Since one star comes from the factory, we must build the other, using the respective plates. 2. Now we must place both stars in parallel, joining the connection points. D. Having both stars, we have a normal part-winding circuit. C. We make the connection to the network, at the ends of each circuit. And remaining for each coil a voltage of 115 volts. When you need to connect a part-winding motor in star-star connection, we must do the following analysis. 2. Internally we already have a star connection. B. Now we are going to form the other star by joining terminals 4, 5 and 6. C. We proceed to supply current to the sleeve that we have just formed. To do this we connect the cables at the ends that will be points 1, 2 and 3. D. Once the start has occurred, after approximately 1 second, current is supplied to the star that had yet to be energized, terminals 7, 8 and 9.